Good morning, everyone. My name is Csaba Györgyi. I'm a PhD student at the Eötvös Loránd University in Hungary. I am going to present an in-network solution for velocity control of industrial robot arms. Our primary motivation for this project is cloud robotics. Moving industrial tasks to the cloud has several benefits. We can access more powerful computing resources, for example for machine learning tasks. It has lower maintenance cost. It is much easier to increment external sensor data. Not to mention, implementing collaboration and interaction scenarios is much simpler. Moreover, one can achieve higher reliability by creating multiple instances. This all sounds great, but where is the challenge? Well, in the original setup, every robot control-related process ran on the robot or next to the robot. If we move all of it to the cloud, we face relatively huge latency, which is not suited for efficient and precise robot control. Okay, but what about edge cloud? Of course, it might solve most of the delay issues. However, because it uses the same virtualization techniques, it still introduces additional latency and jitter that could hurt the strict real-time requirements of the robot. Probably the best way is to keep the low-level, time-sensitive control tasks close to the robot and move only the high-level tasks to the cloud or edge cloud. It can be done, for example, by having fairly intelligent robots equipped with a small computer or by using a PLC. Our approach is the same, but instead of a secondary brain, we perform these computations inside the network. For those unfamiliar with in-network computing, I would like to briefly introduce the P4 language, which we use to implement our data plane functionality. A P4 program describes how an individual packet is processed. It starts with a parser, then a series of match action tables and arithmetic operations follow. Finally, the parser assembles the packet again. Basically, we wish to perform low-level robot control tasks using tables and other arithmetic operations, where normally networking-related tasks are performed. The constraints of the P4 language and the P4 capable devices makes this more challenging. To summarize the main challenges, satisfying the real-time requirements of a robot is not trivial. We need both low jitter and low latency at the same time because we need to send low-level commands, for example velocity vectors, every 2 milliseconds or even more frequently with up-to-date information. The high-level overview of our solution is the following. We assume that a robot is a set of very simple actuators. In the case of a robot arm, these are joints. Each actuator reports its state periodically, which contain the current joint position and velocity. They also require commands at a predefined rate containing the expected new velocity. To keep things simple, we assume a UDP-based communication. I will talk more about it a bit later. And our main concept is that the remote or edge cloud is responsible only for non-time-sensitive high-level tasks. It plans the trajectory and sends the trajectory points to the P4 device, which fulfills a PLC-like role. Let's take a closer look at each component. A robot arm is a set of joints. They report their current status separately, and they receive control messages separately. As I mentioned, we use UDP-based communication, and the values are already in an integer format. The P4 switch has two main roles. It acts like a buffer, storing and maintaining the trajectories received by the industrial controller, and it also performs a low-level velocity control. For technical reasons, determining the current trajectory point is done on the ingress, while the PID-like control is done on the egress pipeline. And finally, the industrial controller needs to worry only about the planning. I promise to talk more about the protocol, because it can make our lives much easier or even impossible. Since P4-capable devices are not usually suited for deep packet inspection, every robot control-related field must be close to the beginning of the packet. P4 language doesn't support floating point arithmetic. Although it is possible to implement certain conversions and operations, it is just much simpler and more efficient to use a decimal format. Moreover, it is much simpler if the status and command messages have the same structure. Based on these considerations, the payload of our packets has the following fields. We have a robot ID and a joint ID. We have the joint velocity, containing the current speed of the joint in case of a status message, or the required new velocity in case of a command message. And we also have the current joint position if it is a status message. One of the biggest puzzles is storing the trajectories in the data plane. Trajectories and their state are encoded in match action tables and registers. Each trajectory point has an ID. Instead of timestamps, we store the duration of each trajectory point, after which we step to the next one. We also store the next trajectory point's ID, thus creating a linked list-like structure. For example, if we are robot number 55, approaching trajectory point number 59, we know that the next trajectory point ID is 60. The figure highlights this with red circles from 1 to 3. But there is more. Thanks to this linked list structure, we can easily override the next trajectory point with a second table called trajectory switcher, which opens up many new opportunities. We can do many fun things with this trick. First of all, we can switch to a different trajectory. We can repeat the same movement over and over again. And if we loop back a trajectory point to itself, it can also stop the robot's movement. After deciding which trajectory point to target, we can continue with the PID-like control on the egress. The new required velocity is basically the weighted sum of three components: the current velocity, the expected velocity, and the difference between the current and the target position. We approximated the multiplication using longest prefix matches. Although we approximated only a simple multiplication, it could easily be a nonlinear function as well. The best thing about this approach is that the higher absolute error for higher values is acceptable in our use case, since a higher input implies that we are far from our goal. We also created a proof of concept implementation of our solution. We choose a robot arm from Universal Robots with 6 joints. We also implemented a plugin for the robot to enforce our protocol. We used an Intel Tofino-based switch, where we used the barefoot runtime for the control plane functionality, and of course P4 for the data plane. Our industrial controller was a Roche instance, which is well known in the automation community. Here we also needed a plugin to interact with the P4 switch. I would like to highlight that although we use Tofino, the P4 device doesn't have to be a switch. It could be a SmartNIC or any suitable device. We believe that if we succeeded implementing these functionalities on a Tofino, they can be implemented on more flexible architectures as well. Thanks to our prototype, we were able to do some measurements. Many measurements in fact, but I think the most interesting ones are the following. How precise is our robot control? What are the side effects of background activities performed by the switch, for example, forwarding other traffic? And finally, the scalability and resource usage related questions. About precisely following the trajectory. I would say it is convincingly precise and the robot arm does what it should. Of course, the Roche controller is currently more precise. However, we think of our solution as an enabler technology. The main advantage of our solution is not its higher precision, rather the opportunity for a remote controller. One might be concerned whether the background activities of the switch could negatively influence the performance of the communication. If you have background traffic next to the status messages, the response times are much worse. However, once we use the strict priority queuing functionality of the traffic manager, this problem disappeared. The second related concern could be whether continuously uploading trajectory points by adding and removing table entries could have any unwanted side effects. Based on our micro benchmarks, this is not a problem at all. We are happy to say that most of the required resources change linearly with the number of robots. We also investigated many other scalability aspects and did other measurements, for example, related to synchronization tasks, but I hope I was able to give you a quick overview. To summarize our work, we introduced a P4-based in-network robot controller that is able to store and follow trajectories, switch between different trajectories, repeat tasks over and over again, or even stop the movement. Moreover, it can do basic synchronization and perform a PID-like control as well. We also implemented a proof-of-concept prototype using a UL robot arm, a Roche controller, and a Tofino ASIC as a P4 device. I also included a small video about one of our tests. After uploading the trajectory using Roche, we see a robot arm drawing a lamp. Finally, I would like to thank you for your attention, and if you have any questions, I am happy to answer them.